Hello everyone and welcome to this module on continuum mechanics. We are moving toward the end of the third chapter, which was about the kinematic of the continuum, mostly hovered around the strain and deformation tensors. So far, we discussed different representations of deformation tensors. We introduce FBC tensors as well as, E star, small E star, the Eulerian strain tensor, and different, you know, uh, deformation tensors that you can use for different implications. But one thing which was common among those, deformation tensors was their representation. So we use the Cartesian coordinate system for both the form and on the form, or the current and reference configurations. Here we're going to establish the relationship for somehow the most important uh, tensors we introduced so far in different coordinates. So, for example, you might have a plate like this. So, it's better to use, Cartesian coordinate system here. This is your initial coordinate system. So you have, let's say, x1, x2, and x3. And then this is your reference configuration. And suppose that you roll this plate to become cylinder like this. And here it's better to use the cylindrical coordinate system. Here you have z, we have, it's better to write it down here. So we have z in here, then we have r, and suppose that theta is increasing in this direction. So here, your current configuration is basically cylindrical coordinate. Or it could be, for example, you can have cylindrical coordinate in the reference configuration, and you also have cylindrical coordinate in current configuration. Or this could be spherical coordinate. So you have spherical coordinate in the reference configuration, and then you have, for example, a cylindrical coordinate in the current configuration. So you need to establish the appropriate relation for uh, deformation tensor for the left and right Cauchy strain tensor. And if I write all of these in a, let's say, in a table, and if I call this reference configuration here, and then we have here the current configuration. So here you have the Cartesian coordinate, and this here could be, for example, Cartesian. These are all the things that we established so far. It could be cylindrical, or it could be, spherical, or any kind of, curvilinear coordinate system. Or here you can have cylindrical, and then you have Cartesian, either Cartesian, cylindrical, or spherical for the current configuration. Here you could have spherical here, and then for your current configuration, you could have Cartesian, cylindrical, or spherical coordinate system. And basically, you have here nine kind of, choices for your reference, as well as for the combination of reference and current configuration. All right, so today we're going to get into uh, the cylindrical coordinate system for both the reference and current configuration. So it means that for both the reference and the current configuration, we have the cylindrical coordinate system, and we are going to find the related equations for for F, B, and C uh, tensors. All right, so let's get started. So suppose we already said that we have xi, this is small x, is equal to xi, capital Xj, and t. Here, this was for the Cartesian coordinate system, but we can simply extrapolate this to the cylindrical coordinate system. So for the cylindrical coordinate system, we have r is equal to r, and here small we can write this as capital R, capital theta, and capital Z, for example. But the book actually used R0, theta 0, and Z0 for the reference configuration here. So this refers to the reference configuration or the material coordinate, and R here is for the spatial coordinate or the current configuration. And then we have t. Then we have theta, which is a function of r0, theta 0, z0, and t. And then finally we have z, which is a function of z, r0, theta 0, z0, and then t. So first of we're going to find f inverse. So if let's get it started by calculating f. So the deformation gradient. All right. So here, if you remember, we had d small x is equal to fd capital X. And for the cylindrical coordinate, we basically had d small x and a vector. Let's put this arrow in here. It's dr er plus r d theta e theta plus dz ez. D capital X was dr0 er0. So we don't put this 0 in here. The book put this 0 in here on the top as a superscript for the unit basis. And then we have r0 d r0 d theta 0 e theta 0 plus d0 ez 0. All right, here we have these two vectors in here, and we have to find the corresponding f. So here we have, so if I write d r, r d theta, and then we have dz, which is equal to this FRR. If you remember, we filled in vertically. So we have theta r in here, and then we have FZR, FR theta, theta theta, FZ theta, and then we had FRZ, F, theta z, and FZZ. So these are the things that these are different components for the deformation tensor that we wrote uh, in matrix form. Then we have dr0, we have r0 dr d theta 0 here, then we have d z 0. So if I do the multiplication, then I'm gonna have FRR dr0 plus FR theta r0 d theta 0 plus FRZ d z0. Then I have F theta r dr0 plus F theta theta r0 d theta 0 plus F theta z d z0. FZR dr0 plus FZ theta r0 d theta 0 plus FZZ dz0. So now dr is equal to this, r d theta is equal to this, and dz is equal to this. So dr is equal to, so as I just write, I expand. So we have dr is equal to FRR. So we have this dr0 in here because it's a scalar. Then we have FRR. So instead of FRR, I'm going to write ER dot FER0. So if you remember, F was basically Fij was the partial derivative of xi with respect to capital Xj. So here you can see that the first subscript, it goes to the reference configuration, and the second one, J, goes to the reference configuration. So maybe I'll write it here. So this is the current configuration, and this one is for the reference configuration. Reference. All right. So that's why we are right here ER. So the first one is for the current configuration, and the second one is for this for the, let's say, reference configuration. So maybe it's a good idea to write in here that this in here is EI EJ0 here for the F for let's say change its color to all right. So you see that the first base for the first base or the first subscript for F is in the reference configuration, and the second one is in the in the current configuration, and the second one is in the reference configuration. So this is current, and this is the reference. All right, so I can write this as this. plus, and now I have r0 d theta 0. Then I have er dot f, and then theta is in reference configuration, plus dz0. Then we have er dot f ez0. Then we have d theta, which is equal to dr0 e theta dot fer0 plus, then we have r0 d theta 0. Then we have, we have e theta dot f e theta 0 plus dz0. Then we have the first one is theta, and then we have f e z 0. Next we have dz is equal to dr0 ez dot fer0 plus r0 d theta 0 ez, dot f theta 0 plus dz0 ez dot f ez0. Perfect. So now we have dr, d theta, and dz. So we can get different components for, this is f RR, right? So we can get different components for, let's say, FRR, and then this is, for example, FR theta and the rest. So if I just draw kind of table here. All right, so here you can see that this is FRR, right? So FRR is partial derivative of r with respect to r0, because here d changes to partial because r is a function of r0, theta 0, and z0. So we have to change this d in here to partial, and also in here, because r0 is also a function of r0, theta 0, and z0, and t as well. All right, so, and let me just move this a bit in here. So we have er dot f er. So next we have er f e theta, which is fr theta. Fr theta is in here. So we have er dot f e 0 theta is, so partial derivative of r with respect to r0, partial derivative of theta 0. And then this one in here is er dot f e z 0 is equal to partial derivative of r with respect to z0. Then we have e theta r, f theta r. Theta r is in here. So we have e theta f 0r is equal to partial derivative of theta with respect to r0. It's in here. Then we have e theta that f theta 0 is partial derivative of theta with respect to r0, partial derivative of theta 0. And then we have e theta that f e z 0, which is partial derivative of theta with respect to z0. Next, we have this in here. So e z dot f er0 is partial derivative of z with respect to r0, and ez dot, this is z naught 2, f e0 theta is partial derivative of 0 with respect to r0, partial derivative of theta 0. And then we have ez dot f e z 0 is equal to partial derivative of z with respect to z0. Great. So up until here, we calculated the f, calculated f, the deformation gradient tensor for the cylindrical coordinate. And now we can simply calculate f er0 here. So from here, let me change color. So here you can see that here, if you see er.fer, this is equal to this expression, e theta dot fer0 is equal to this expression, and ez dot fer0 is equal to this expression. So if I write this, and if I, for example, put er dot fer0 is equal to partial derivative of r with respect to r0. So if I multiply, if I dot both by er, so this becomes 1 and this becomes er, right? And if I write the same in here, so if er is equal to partial derivative of theta with respect to r0, then e theta, so this becomes 1, this is this one, and then we have er0 is equal to partial derivative of z with respect to r0, this is ez, because we have ez in here and dot product, so it becomes 1. All right, so now we have this, and we know that fer0 is basically fjrej, if you remember. So it is basically frr, j is r, theta, and z, er plus f, let's say theta r e theta plus f z r e z, which is equal to frr. frr is this one. So it is the partial derivative of r with respect to r0, er, plus f theta r, which is this one, partial derivative of theta with respect to r0, e theta, plus fzr, which is this one, partial derivative of z with respect to r0. Here, we already wrote those. So if we sum this, we get fer0. So we can do the same and write for e theta. So maybe if I just copy this and paste it here. All right, so I can write the rest in here. Fe theta 0 is equal to the sum of these. So it becomes partial derivative of r with respect to r0, partial derivative of theta 0, er. This is the first one, and the second one, partial derivative of theta r0, theta 0, e theta plus. The third one, partial derivative of z with respect to r0, 0, e z. And then I can write f e z 0, which is in here, partial derivative of r with respect to z0 er plus r partial derivative of theta with respect to c0 e theta plus partial derivative of z with respect to z0 e z. All right, so now we have FER0, FE theta 0, FEZ 0. Now let's find F transpose. So I may change this color in here. All right, so we need also F transpose. Why? Because B is equal to F transpose, or for example, C is equal to F transpose F. So far we calculated F, but we also need F transpose. All right, so here we have ER dot FER0 from here, which is equal to partial derivative of R with respect to R0. I'm going to just remove these for the moment. So since this is dot, I can write this as FER0 dot ER. So I can transpose this. I can write this as ER dot F transpose ER. ER0 dot F transpose ER. So this was equal to partial derivative of R with respect to R0. This is equal to F transpose RR. Next, I have ER FE theta FER that FE theta 0 is equal to FE theta 0 dot E, sorry, yeah, that is true. Okay, it is equal to E theta 0 dot F transpose ER. It's partial derivative of R with respect to R0, partial derivative of theta. Here it is. Here is this expression. And next, I'm going to calculate this one. I'm going to use this one. So next I have ER dot FEZ, which is this one in here. It is equal to FEZ0 dot ER. I can write this as EZ0 dot F transpose ER is equal to this expression, partial derivative of R with respect to Z0. And here we have F theta R, and here we have F Z R. And these are transpose, right? So here you can see that this is F transpose theta R. So this is F transpose theta R. So this is F transpose theta R. So since transpose, we swap the columns and rows. So here F theta R goes in here. So if I write it down in here, I'm going to have F transpose like this. So I'm going to have write it this way. All right, so we have FRR remains where it is. Then we have F theta R transpose. So F theta R is in here. So we have to put it here. So we swap these two. So F theta R goes in here. So we have partial derivative of R with respect to R0, partial derivative of theta 0. And then we have partial derivative of R with respect to Z0. So if you want to calculate F transpose ER, it is fairly easy because you have F transpose JR, E J transpose. So here you have the the current configuration here, you have the reference configuration where J is R, theta, and Z. So this is F transpose R R E R 0 plus F transpose theta R E theta 0 plus F transpose Z R E Z 0. Now you have F transpose ZR here, and you have F transpose theta R. So this is F transpose theta R, and this is F transpose RR, F transpose RR. So this is equal to partial derivative of R with respect to R0 ER0 plus partial derivative of R with respect to R0 theta 0 E theta 0 plus partial derivative of R with respect to Z0 E Z0. Perfect. This is F transpose ER. So next we have F transpose E theta. Maybe I can start again from here. So I write the second row. So I have E theta, maybe with another color, E theta dot F ER0, which is this one. So I can write this as F ER0 dot E theta, which is equal to ER0 dot F E theta, which is equal to R partial derivative of theta with respect to R0. Let me check. I guess that I missed something in here, because here we have R d theta. So I have to add R all over here. Yes. All right, that would make sense. And then I have E theta dot F E theta 0, which is E dot E theta. So now this can be written as E theta dot F transpose E theta R partial derivative of theta with respect to R0 partial theta. This one is F R theta. This one is F theta theta. And then I have E theta dot, no, sorry, yeah, it is true. EZ0 is equal to F EZ dot E theta. So this is EZ dot transpose E theta, which is equal to partial derivative R, partial derivative of theta with respect to Z0. This is F Z theta. Therefore, F transpose E theta can be written as Fj theta E theta. And this is, in the current configuration. So this is in the reference configuration. Then we have F, so J is R theta, E theta. Oh, sorry, this is J as well. R plus F theta theta E theta plus F Z theta E Z. So F transpose E theta is equal to, so FR theta is this one, R partial derivative theta with respect to R0, E R0 plus R partial derivative of theta with respect to R0, partial derivative of theta 0, E theta 0 plus R partial derivative of theta here with respect to R Z0, E Z0. All right. Next, we have the third column. So let me fill in here. So I will pause the video and I will write the components for the third row in here, because just writing everything is just repetition. So I just fill in the third row of F transpose tensor in here. So I already wrote them down here. And now we can simply calculate B. So let's go for B, the left Cauchy strain tensor. And here book actually find it, just found B with respect to current configuration. But you can find it with respect to the reference configuration. It solved C for the reference configuration. So, but you can derive your desired equation based on different configurations. So we have B, and we, for example, want to find BRR, right? So we can write ER dot B ER, and since we know that B is basically F transpose, we can write ER dot B, F transpose ER. So we can write this as ER dot F transpose ER. So we have to find F transpose ER, and F transpose ER is in here. So this is F transpose, easy. And this is F transpose E theta. So I have to write down this in here. So I copy this, copy, and then paste it in here. All right. So this is equal to ER dot F. This is F transpose ER. This is F transpose ER. So this is equal to partial derivative of R with respect to R0. I can just take this out, it's scalar. So it's the magnitude. So I can get this ER dot F ER0 plus partial derivative of R0 theta 0. And then I have ER dot F E theta 0 plus partial derivative of R with respect to 0, Z0. Then I have ER F E Z 0. Now I have to find, I have to find I have to find ER dot FER0, or I have to find FER0 FE theta 0 and FZ FEZ0. And the I have to calculate the dot product with ER. So ER0 is already in here. So ER dot this, ER dot this, and ER dot this. So the first one becomes partial derivative of R with respect to R0. So I have this in here, but this becomes the same. Then I have partial derivative of R0, then theta 0. Then ER dot F E theta 0. FE theta 0 is here. ER dot this gives me this, which is partial derivative of R with respect to R0, theta 0. Then R with respect to Z0, then this one is again this. So if I summarize this, this becomes squared plus, so if I take this here. It's become squared plus, if I take this here, squared. So for example, let's solve and find for BZ theta. So it is EZ dot BE theta, which is equal to EZ dot F transpose E theta, which is equal to EZ dot F. So F transpose E theta, sorry, this one, F transpose E theta. We have to find this, F transpose E theta. F transpose E theta, it's here. So let's copy, paste it in here. So then I have EZ dot F. This is F transpose E theta. So then I have R partial derivative of theta with respect to R0, EZ dot F ER0 plus R partial derivative of theta, R0, theta 0, EZ dot F theta 0. Then we have this in here. Then we have EZ dot F, EZ0. So FER0 is already here. So we have to find EZ dot this, then EZ dot this, then EZ dot this. All right. So I have R partial derivative, then ER, this is partial derivative of Z with respect to R0 plus R theta 0, then I have R. Then this one is C with respect to R0 theta 0 plus R 0. Then we have EZ dot F EZ0. So is derivative of Z with respect to Z 0. All right. You can find the rest of components just by following this strategy in here. Let's find B inverse. Again, with respect to current configuration. Current configuration. And remember, current configuration, we mean small x. All right. So if you remember, we had B equal to F transpose. But B inverse is equal to F transpose inverse F inverse, which is equal to F inverse transpose, then F inverse. So I have to find F inverse as well as, you have to find F inverse as well as F inverse transpose. C is also the same because we have F transpose, F inverse, then we have F inverse. Next we have F transpose inverse, which is the same as F inverse transpose. So again, if we find F inverse and F inverse transpose, we can find B inverse and C inverse. All right, so let's first say that F inverse ij, if you remember, it was partial derivative of capital Xi with respect to small xj. And we had dx where it was equal to F inverse d small x, where we had xi was equal to xi small xi and then t. Here we can write the same for r0 was equal to r0, then r theta z and t. Then we had theta 0 was theta 0, r theta z and theta. And z0 was equal to z0 r theta z and t. So simply it means that the first one here, the first subscript, it refers to the reference configuration. And the second one, it refers to the current configuration. All right, and we also know that dx, d capital X and d small x, they follow this in the cylindrical coordinate. So it's a good idea just to copy and paste this one in here. All right, perfect. So basically, F inverse is F inverse RR, F inverse. So let's just fill it in. So we know that we have to write it as this. So F theta R, and then F inverse ZR, then F inverse R theta, F inverse theta theta, F inverse Z theta, F inverse RZ, F inverse theta Z, and F inverse, sorry, ZZ. So we had this F inverse in here, and this should be time dr, r d theta, and dz to give dr0, r0 d theta 0, and then dz0. This is equal to F inverse RR dr plus F inverse, and maybe it's a good idea just to write, to again mention that here we're dealing with EI0, and then we have EJ. So the first one is in reference, and this one is in current configuration. All right, so we have F inverse R theta, R d theta plus F inverse RZ dz. Then we have F inverse theta R dr plus F inverse theta theta R d theta plus F inverse theta z dz. F inverse zr dr plus F inverse z theta r d theta plus F inverse z z dz. So dr0 is equal to this expression, the first one, r0 d theta 0 is equal to the second row, and dz0 is equal to the third row. So I have dr0 equal to F inverse RR, but I'm going to write it down like ER because we know that first subscript that goes to the reference, so ER0, then we have F ER, this is F inverse, right? F inverse ER dr plus, then we have F inverse R theta. So it is ER0 dot F inverse E theta R d theta plus E R0 dot F E Z F inverse F Z dz. All right. So like previous, we know that, let me Okay, like previous, we know that dr, since r0 is a since r0 is a function, let me do it here, is a function of r theta, z, and t. We have dr0 is a function of uh, r0 with respect to r, dr, plus partial derivative of r0 with respect to theta, d theta, plus partial derivative of r0 with respect to z, d, z. So we're going to compare these two together. So it's the same strategy we utilized in here. So by comparing these two, we get, let me just draw. Okay, so we have, if dr in here, so this one is equal to this one. So er0 dot f inverse er is equal to partial derivative of r0 with respect to r in here. Then we have f, so r theta. So we have r theta in here, r theta. So we have to write it in here. So er0 dot f inverse e theta is equal to partial derivative of r0 with respect to r, partial derivative theta. Then we have r, this one, r0 dot f inverse ez is equal to this one component. Okay, in here. Next, we have r0 d theta 0 is equal to, here, the second row. So it is it is e theta 0 dot f inverse e r. This is theta r. The first one is, the first subscript is in reference, and r, the second one, is in the current configuration. That's why we put 0 in here and nothing in here. So we have f inverse er dr plus e theta 0 f inverse e theta r d theta plus e theta 0 dot f inverse ez dz. So again, we know that d, like here, d theta 0, since theta 0 is a function of r theta and z, so it's become the partial derivative of theta 0 with respect to r dr plus partial derivative of theta 0 with respect to theta d theta plus partial derivative of theta 0 to z d z. So by comparing these two, you can get that f inverse theta r, which is basically this one. So e theta dot f inverse er is equal to this partial derivative divided by r0. Sorry. So r times r0. This is equal to r0 partial derivative theta 0 with respect to r. So if we compare these two terms together with this in here, we get e theta 0 dot f inverse E theta is equal to R0 partial derivative theta 0, R, this one here, and then we have F inverse Z is equal to R0 respect to Z. Okay, I fill in the third row. I will pause the video and fill in the third row. All right, so now we filled in the third row here, and here are the relevant calculations. So now we have to find F inverse. So we have to find F inverse ER and F inverse E theta and F inverse E Z. We utilize the same strategy as before. So here we have we have to use the dot product here, and then we have F inverse ER. It is ER dot this is equal to to this expression, then E theta, then E Z 0 here. So we have F inverse JR EJ 0, because here we have theta dot 0, ER 0, and EZ 0. And here and J is R theta and Z. The same strategy we utilized in here. So I'm going to write this again, but instead of FER 0, I'm going to find F inverse ER 0, ER. All right, so we have F inverse RR ER 0 plus F inverse theta R E theta 0 F inverse ZR E Z 0. This is equal to partial derivative of R0 with respect to R, because this is RR, RR is this one, then we have theta R, which is this one, and then we have ZR, which is this one. All right, so we have ER0 plus inverse ER plus R plus F inverse theta R, R0, theta 0 plus, this is Z0, respect to R, 0. Next, I have F inverse E theta, which is Fj theta inverse EJ0. So it is F inverse R theta ER0 plus F inverse theta 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 0 plus F inverse Z theta EZ0. So F inverse E theta is equal to partial derivative R0 with respect to R plus R0, then R partial, then so this is the second equation, and then I have to find F inverse Fz, which is F inverse Jz EJ0, which is F inverse RZ E R0 plus F theta Z E theta 0 plus this inverse F inverse Z Z E Z 0 is equal to, so F inverse E Z is equal to F inverse, sorry, A is equal to F inverse RZ, which is R0 with respect to Z, ER0, plus RZ is this one, and this is theta Z. So theta Z is R0 and then partial derivative of Z0 with respect to Z, EZ0. So now we found out F inverse EZ as well, and we need to find F inverse transpose. F inverse transpose here. So F inverse transpose, we have to find this. Okay, we can use F inverse ER in here. So if I have, for example, this component here, ER, 0 dot F ER, F inverse ER, this one in here. So it's better to just copy this one or copy to paste it here. So I have this one. I remove this one. So I have F inverse ER dot ER 0. I can write this as this is equal to ER dot F inverse transpose ER 0. This is equal to partial derivative of R0 with respect to R. This is F inverse transpose RR component. Then I have this one. So you copy and I paste in here. So if we get rid of this, so you have F inverse ER dot E theta 0 is equal to ER dot F inverse transpose E theta 0 is equal to, it was R0 partial derivative of theta 0 with respect to R. So this is FR theta, F inverse transpose R theta. All right. So next, I copy, paste this in here. See, okay, so I can write this F inverse ER dot EC0 is equal to ER dot F inverse transpose EC0 to, so this is partial derivative of Z0 with respect to R. So this is F inverse transpose RZ. So F inverse transpose RZ. So if I can find F, so this RZ, this should go in here for the transpose. So I will calculate the rest. So I have to pick this one, or I may select all of these, copy, and paste them here. So I will let me just copy these as well, and then paste them here. Okay, I will pause the video and I will write these. All right, so now I have derived all the relevant equations in here for the different components of F inverse transpose. So if I just want to write F inverse transpose in here, so we're going to have F inverse transpose, RR. Then we have R theta here, but we have theta R because it is transposed. F inverse transposed, CR, inverse transpose. Here we have r theta should come here. Then we have F inverse transpose theta theta. Then F transpose F inverse transpose Z theta. And then we have F inverse transpose RZ, F inverse transpose theta Z, F inverse transpose Z Z. All right, so now let's find different components for F inverse transpose ER0 here. F transpose, for example, here, this one. So F transpose, F inverse transpose ER0. So here we have ER, so I utilize the same strategy. F inverse transpose JR EJ is equal to F inverse transpose J is R theta and Z, RR ER plus F inverse transpose theta R E theta plus F inverse transpose ZR E Z. So this is equal to, so F inverse transpose RR is this one, F inverse transpose RR. So this is the partial derivative of R0 with respect to RER plus, so F inverse transpose theta R. Theta R is this one. So partial derivative of R0 R theta plus. Then we have F inverse transpose ZR. Yes, it's this one. Partial derivative of R0 with respect to Z, E, Z. Then I have to find F inverse transpose E theta 0, which is F inverse transpose J theta E theta. So F inverse transpose R theta, oh sorry, this is J R plus F inverse transpose theta theta E theta plus F inverse transpose Z theta E Z. So equal to, okay, we have F inverse transpose R theta, which is this one, R0 partial derivative of theta 0 with respect to partial derivative of RER plus F inverse transpose theta theta, which is this one, R0. And then we have F inverse transpose Z theta, which is this one. So R0 theta 0. So I will pause the video and find F inverse transpose E Z0. So now we have the equations for F inverse transpose ER0, E theta 0, and E Z0. So now we can simply calculate, for example, B inverse R theta, for example. This is ER dot B inverse E theta, which is equal to BER dot, this is FF transpose inverse E theta, which is equal to ER dot F transpose inverse, F inverse transpose, then we have F E theta, F inverse E theta. So F inverse E theta is basically here. F inverse E theta is in here. So I need to copy this. Paste it here. So I have E is equal to ER dot F inverse transpose this expression here. So I'm going to get ER dot, so partial derivative of R0, R theta, then I have ER F inverse transpose ER0 plus R0 partial derivative theta 0 R ER dot F inverse transpose. Then I have E theta 0 plus partial derivative of Z0 R partial derivative of theta. Then I have ER dot F inverse transpose EZ0. So now I need to find F inverse transpose ER0. F inverse transpose ER0 is this one here. So if I copy this, and if I paste it here, so this one is here. So ER dot this only leaves us with this component in here. We follow the same, the rest of the terms. So we have R0, R theta. So this one was partial derivative of R0 with respect to R. Then we have R0 partial derivative theta, R theta. And then this one again is R0 theta 0 partial derivative of R plus again this one Z0 R theta. Then we have partial derivative, and this one is partial derivative of Z0 with respect to R. All right. So now let's calculate. You can calculate basically B with respect to X with the reference configuration. But here the book actually calculated C with respect to reference configuration. X, capital X. So here, we already know that, again, I can copy this. Paste it down here. So we know that xi, small xi, is equal to a small xi, which is a function of capital Xj and t. And here we have the cylindrical coordinate, right? So if you want to calculate, for example, CR0 theta 0 here, so the book used 0, 0 in here to show that we are deriving basically this component CR theta with respect to the reference configuration. So this is equal to ER0 dot theta 0, which is equal to ER0 dot, so C is F transpose F, E theta 0, which is equal to ER0 dot F transpose F E theta 0. And F E theta 0, we have to find this. F E theta 0, F E, here it is, F E theta 0. So we copy this. And we paste it here. So I have equal to ER0 dot F transpose this whole expression here. All right. So next, we have to write partial derivative of R 0 theta 0. Then we have ER0 dot F transpose ER. Let me just get rid of these hats. You know that these are bases, unit bases, plus partial derivative of this F transpose E theta plus partial derivative C 0. This is ER0 dot F transpose E Z. And F transpose ER is already in here. F transpose E theta is here. F transpose ER is also here. And F transpose E Z is also here. So we have to find ER dot. So ER dot this is just it just leaves us with the first term. Then again, ER dot just leaves us with the first term, and ER dot F transpose EZ just left us with the first term. So here it goes. Partial derivative R, R0, theta 0. Then this one is partial derivative of R with respect to R0 plus this is sorry, I think that I missed something in here, like an R. So if I go to yes, these all have R, I guess. These all have R. So this also has R. So yes, we have, and then we have this, which is the first term. All right. Then we have this. All right. You can calculate the rest of the terms using this strategy. So let's find C inverse components. Again, the book said we're going to find this with respect to the reference configuration. Capital X. So we have C inverse R0 theta 0. So it is ER0 dot C inverse E theta 0 is ER0 dot. So F transpose F inverse E theta 0 is equal to ER0. So we have F inverse, then we have F inverse transpose, or F transpose F transpose inverse, then it becomes F inverse transpose, then E theta 0. So first we have to find this F inverse transpose E theta 0. F inverse transpose E, here it is, F inverse transpose E theta 0. So we copy this and we paste it here. Awesome. So this one is ER0 dot F inverse. This expression is this one. So we have R0 partial derivative theta 0 R ER0 dot F inverse ER plus R0 theta 0 R theta. We have ER0 F inverse E theta plus R0. Then we have ER0 dot F inverse E Z. So now we have to find F inverse ER. F inverse ER. F inverse ER is this one. So we're going to find basically ER0 dot this F inverse ER. So ER dot this, ER dot this, and ER dot this, which leaves us with the first terms in here. So this is R0 partial derivative theta R. Then this is basically R0 R plus 0 theta 0 R0 R theta plus R0 theta 0, then Z is partial derivative 0 with respect to Z. All right, we now calculated C inverse with respect to the configuration X. We can use the same strategy to calculate the different components of C inverse with respect to the reference configuration as well as the current configuration.